We've discussed how overfitting is the central obstacle that we face when training machine learning models. And we've discussed a few different ways to prevent overfitting. The best way, if you can do it, is to get more training data. Another option, which is maybe the simplest option, is just early stopping. And another option that we discussed is to reduce the complexity of our neural network. Use a smaller architecture, maybe use fewer layers, or use fewer nodes per layer. That makes our network less flexible and less prone to overfitting. And then another important option that we've discussed is regularization. We can use regularization when we're training the neural network. And we discussed L2 regularization, which is very common, very fundamental. We also discussed L1 norm regularization. And there's a third type of regularization, which is very important, which is called dropout. And the way dropout works is when you're training your neural network using stochastic gradient descent, at each epoch, before you compute your gradient, you randomly omit a subset of the nodes in your neural network before you compute your gradient. You just randomly drop them out. So maybe 50% of the nodes in your neural network are just omitted. We pretend they don't exist. And then we take the derivative, we compute the gradient. And then we do that again at each iteration of stochastic gradient descent. That procedure has the effect of preventing overfitting. It's a very successful and popular regularization procedure. Somehow when we do this, it's like more difficult for the neural network to exploit special quirks in the training data, and it has to somehow find patterns that are more robust, and those more robust patterns are more likely to generalize. And if you read the book we've been following, Deep Learning with Python by Francois Chollet, there's a section where Jeff Hinton tells the story of how he thought of dropout, and I'm just going to read what Jeff Hinton said. "I went to my bank. The tellers kept changing, and I asked one of them why. He said he didn't know, but they got moved around a lot. I figured it must be because it would require cooperation between employees to successfully defraud the bank. This made me realize that randomly removing a different subset of neurons on each example would prevent conspiracies and thus reduce overfitting." So in this video, I want to observe the effects of these various regularization procedures, in particular, reducing the size of our neural network, and also L2 regularization, and also dropout. And we're going to use the IMDb movie review classification example, which we looked at previously. So here's a section of code where we're just reading in the data. The data set comes with TensorFlow, so it's very easy to load the data. We're keeping the 10,000 most popular words in the collection of movie reviews. And here's our code, just like before, that vectorizes the movie reviews. So each movie review is described by a feature vector with 10,000 components. And each component of that feature vector just tells you whether or not the corresponding word in the dictionary appears in this movie review. And then we're going to take 5,000 of our examples in our data set and make them into a validation data set. And then the remaining examples are going to be used to train our model. Remember, stochastic gradient descent is not allowed to look at these 5,000 examples that are in the validation data set while it's training. Now here we are specifying the architecture of our neural network. This is exactly the same architecture we used before when we did IMDb movie review classification. So we have a dense layer with 16 nodes, each using the ReLU activation function. Then there's another dense layer with 16 nodes, also using ReLU. Then there's finally a output layer, and we use the sigmoid activation function because we're doing a binary classification problem. And then when we compile this model, we're telling TensorFlow to use the RMS prop optimization algorithm, use the binary cross entropy loss function. That's what we use for binary classification. The metric that we're going to keep track of is classification accuracy. And then here we're specifying the architecture for a smaller neural network. So here the first dense layer has only 4 nodes instead of 16. And the second dense layer has also 4 nodes instead of 16. So this is a much smaller network, so it's much less flexible. That should make it less susceptible to overfitting. And then here is a final network that's like too large. This is a much larger network. The first hidden layer has 512 nodes. The second hidden layer has 512 nodes. And then the final output layer, again, uses the sigmoid activation function. It has just a single node. Let's train each of these three models. So we're training the first, we're training now our original model. As usual, this would be faster if we were running the code on a GPU. It's just running on my CPU, so it's a little bit slow. So we just finished training our three models, and what I want to look at now is a plot of the validation loss at each epoch for both the original model and the smaller model. What we're calling the validation loss is what you get when you evaluate the objective function using the validation data set. So let's take a look at these plots. Okay, and here you can see the smaller model begins overfitting later, and it's less prone to overfitting. This illustrates the fact that smaller models because they're less flexible, they're less prone to overfitting. On the other hand, we have to be careful that a smaller model might underfit the data. It might not be flexible enough to capture the meaningful patterns in the data, the patterns that will generalize. So we have to try to find a sweet spot in terms of model complexity. Next, let's look at a plot of the validation loss at each epoch for the original model and for the larger model that had 512 nodes in the first hidden layer and 512 nodes in the second layer. Let's take a look at this plot. So you can see that the larger model begins overfitting earlier and the overfitting is worse. So finally, let's look at a plot of the training loss at each epoch for both the original model and the larger model that has 512 nodes in each hidden layer. What I'm calling the training loss, that's what you get when you evaluate the objective function using the training data. So let's take a look at this. And we can see here that the larger model, which has like a very high capacity, it's very flexible, it's doing great at explaining the training data. But even though this model is getting a training loss of almost 0 on the training data, that doesn't mean it's a better model because this model is overfitting and it's doing worse when we look at the validation data. So far, we haven't used regularization yet. All we've been doing is just changing the size of our model. Now let's try actually using regularization. So here's a section of code where we're just defining our original model. 16 nodes in the first hidden layer, 16 nodes in the second hidden layer. This is our original model. And here is a section of code where we're using the same architecture, but we're telling TensorFlow that TensorFlow should use L2 regularization when training this model. We're going to use L2 regularization on the weights in the first layer, and we're also going to use L2 regularization on the weights in the second layer. So let's train both of these models. It's the same architecture. The only difference is that in the first case, we're not using regularization when we train the model. And in the second case, we are using L2 regularization. This hyperparameter, 0.001, tells us how heavily the L2 regularization term is weighted in our objective function. The larger this parameter is, the more heavily weighted our L2 regularization function is. So we finished training both of our models. Now let's look at a plot of the validation loss at each epoch for both models. Okay, so we can see that the model that was trained using L2 regularization is being less affected by overfitting. So we can see the effect of L2 regularization in this example. Now let's try using Dropout. Here we're specifying the same neural network architecture, and we're telling TensorFlow that while it's training this neural network, TensorFlow should use Dropout on the first hidden layer and also on the second hidden layer. What this 0.5 means is that at each iteration of stochastic gradient descent, before we compute the gradient, 50% of the nodes in the first hidden layer and in the second layer selected at random are going to be omitted from our neural network, and we're going to compute the gradient pretending that those nodes don't exist. We're not going to use L2 regularization when we train this model. We're just going to use dropout. So let's train this model. Okay, we finished training our model. Now let's look at a plot of the validation loss at each iteration for both our original model, where we didn't use any regularization at all when we were training it, and also our current model where we used dropout. Okay, so you can see that the model that was trained using dropout, it begins to overfit later, and it's less severely affected by overfitting.